Good day and welcome back. In this video, we will begin our discussion of something called the dot product. Now, the idea is that in the previous section when we discussed vectors, we explored them from both this geometric and analytical perspective. And specifically, we looked at the operations of vector addition and scalar multiplication. And hopefully that left you wondering, how do we take a product of two vectors? And we will explore two ways of multiplying vectors together, the first of which is the so-called dot product. So to begin, let's look at how we define the dot product of two vectors. So in order for us to take the dot product of two vectors, A and B, the only restriction that we have on them is that they have the same number of entries. And the dot products of A and B, it's very important to think of the quantity we're working with, is going to be a number or a numerical value. And how it is defined is we multiply together the corresponding entries and then we add them up. So A1B1 plus A2B2 plus A3B3. And note that it really only matters that we have the same number of entries so that we can perform this operation we've defined above. So if we had vectors with two entries, so let's say A1, A2, and we wanted to dot that with B1, B2. We multiply together all of the corresponding entries, A1 times B1, and then we add them up, A2, B2. So let's look at a specific example or two here. If we had the vector 1, 3, and we wanted to dot it with minus 2, 1. We multiply together those corresponding entries, and then we add them up. So in this case, we would have minus 2 plus 3 is positive 1. Similarly, just to illustrate, it doesn't matter how many entries. If we had the vector 0, 1, 2, dot it with the vector minus 1, minus 2, minus 3, we multiply together those corresponding entries, and then we add them up. And in this case, we have 0 plus minus 2 plus minus 6, so we get back minus 8. So the observation I would like to make here is that calculating a dot product is something that is easy computationally. So I think we can all agree multiplying some numbers together, adding them up is not a difficult task. But the real question that we have is, what does this number tell us? That is, it's very easy to compute the number, the dot product of these two vectors, but what does it mean? What does it tell us about the vectors? So in order to begin investigating that, the first thing I'm going to do is look at what we might think of as some basic properties of the dot product. So if A, B, and C are vectors that all have the same number of entries so that we can dot them together, and C is a scalar. And note I've purposely used C here in two roles. The C with an arrow over it indicates it's a vector. The C by itself indicates that it is a scalar. So a few properties of the dot product. A dotted with A is always going to be the magnitude of A squared. A dotted with B is equal to B dotted with A. And as a side note, we can prove, or maybe we'll say just explain why these properties are true simply by going back to how we have defined the dot product. And if we think about the order we multiply or add, we see it doesn't matter. So A dotted with B is B dotted with A. Furthermore, we can take this dot product and we can distribute it across vector addition. That is, we could write this as A dotted with B plus A dotted with C. And the 0 vector dotted with any vector should be the number 0. So we will think of these as being just the basic properties of the dot product. And whenever we encounter them moving forward, we will use them freely without justification. So now on to what I might think of as a geometric property, or we could even think of it as an alternative definition of the dot product. If theta is the angle between A and B, and I'm going to draw kind of a little picture to go along with this. If we have a vector A, maybe say a vector B, theta would be this angle between them. Then in this case, the dot product is defined as, or we have this property, A dotted with B is the magnitude of A times the magnitude of B multiplied by cosine of the angle in between. And just an observation as to why this might be useful, let me just note that this allows us a way of computing an angle between vectors. If you were to isolate the cosine of theta, it would be A dotted with B divided by the magnitude of A times the magnitude of B. And this is a formula that we would use to find the angle between two vectors. And you can get to that theta by taking an inverse or an arc cosine of both sides. And we'll investigate that in a moment. Now, a common question that one might ask is, we have this nice formula, this geometric property of the dot product. Where does something like that come from? And just to give you a small bit of intuition without going into details, if we look at the picture we've drawn here to the right, if I was to draw the vector going from the terminal point of B to the terminal point of A, think for a moment, what vector is that? And we discussed this in the previous section. It's the vector A minus B. Think about it intuitively. A minus B plus B gives you back the vector A. I just realized this needs a vector. And we can prove, or we can come up with this by applying the law of cosines. So applying the law of cosines, which you may recall from, say, a trig or a pre-calculus class, gives the property that we want. And if you're intrigued by that idea of applying the law of cosines to come up with our property, I recommend taking a look in the book and thinking about those details. So let's go ahead and apply it. Let's find the angle between the vectors given by A and B. And this is a point that if we were in class face-to-face working together discussing the dot product, I would ask you all to take 4 or 5 minutes, turn your desk, work with your neighbors, find the angle between these two vectors. So I suggest we do the same thing here. Feel free to pause the video and take a few minutes and see if you can apply this geometric property above. Okay, so assuming that you've taken a few minutes to apply this above geometric property, and if not, do so, let's go about finding this. So note from above, and I'm leaving some space to add in some details, cosine of theta would be A dotted with B divided by the magnitude of A and the magnitude of B. So if we can determine 3 key ingredients, the number A dot B, the magnitude of A, and the magnitude of B, we can use that information to solve for theta. So let's go ahead and calculate those. So let's first work with our new quantity. A dotted with B would be 3 times minus 2 plus minus 1 times 4 plus 5 times 3. So we have minus 6 minus 4 plus 15, which would give us a positive 5. The magnitude of the vector A, remember the magnitude of a vector is defined to be the square root, and then underneath the square root we add up the sum of the components squared. So 3 squared plus minus 1 squared plus 5 squared. So that would be the square root of 35. Similarly, the magnitude of B would be the square root of minus 2 squared plus 4 squared plus 3 squared. So the square root of 29. So cosine of the angle theta that we're hoping to solve for is 5 divided by the square root of 35 times the square root of 29. Now, it turns out this is not going to be a nice angle. It's not going to be something like pi over 6, pi over 4, pi over 3, or multiples around the unit circle, but we can still write out the exact value for this. If we isolate that theta, it's going to be the inverse cosine of 5 divided by the square root of 35 times the square root of 29. And I would leave the angle exactly in this form. And just as kind of a side note, because I believe this is the first time we've encountered an inverse trig function, you could also write cosine inverse, but I oftentimes will choose to write arc cosine whenever possible, just to make sure we don't incorrectly assume this -1 as indicating a reciprocal opposed to the inverse. So once again, leaving it in this form gives us an exact value. If you plug it into your calculator, it would simply be a decimal approximation. So in the next video, we are going to continue on with this idea of properties of the dot product. So stay tuned and take care.